Welcome everyone. Good morning. Thank you for tuning in. So today, myself and Danny will be discussing DfMA, specifically related to glue laminated timber, primarily around connection detailing. Just a little bit of background on Ash. So Ash is a sawmill that has been operating for over 100 years. It's now an amalgamation of many smaller Victorian timber mills, and with the location in Hayfield. And you can see here, this is an aerial view of the Weir Road manufacturing facility. We also have a few kilometres down the road, the Green sawmill. So it's a very, very large operation overall, as you can tell by just the scale of this aerial shot. And yeah, Ash has been now manufacturing for over 30 years and producing various timber products, including doors, window frames, staircase components, lining and cladding boards, and now the Maslam glue laminated timber line for structural components. We also have a new massive engineered flooring line or plant coming online, and that'll be Australia's only fully integrated pre-finished engineered floor line. So that's really exciting and just really emphasises the wide range of what we can supply for all project needs. We have a Hundegger speed cut as well as the K2I. So this is an image of the K2I, which is the largest and most efficient new generation Hundegger CNC machine. And we also have a second one coming online soon, just to really increase our manufacturing capabilities. Here's some images just of some projects that we've delivered to just once again highlight the various timber products that we manufacture and supply for projects. You can see here just a number of them. We've got many more. Go to our website and our Instagram page for more views of all of this stuff. And here you can see just what can be achieved with Maslam GLT. This is the Latrobe Arts Centre project. And yeah, utilising some engineered trees essentially, which is a really beautiful way to use structural elements. Well, I think so anyway. And while I think of it too, we are hiring looking for some local Hayfield or the surrounding Gippsland area carpenters. So if by chance any are tuning in today, or if you know any that are, please get in touch with us. All right, so getting into it. Design for manufacture and assembly. Essentially, to me, that, like I said here, that's optimizing designs to essentially minimize effort while increasing productivity and reducing cost, and then enhancing speed, efficiency, safety, quality, and sustainability of the product. And when we look at the sort of the key stakeholders on any given project, and the client would sort of fall under the builder or architect here, primarily, there's always different drivers by all stakeholders on a job. Everyone has their own challenges and their own needs and desires for what they believe they need to achieve to have a successful project, essentially. So what I'm trying to show here is that there's that sort of Goldilocks zone, or there's that sort of mutual area where everything aligns and you get the best outcome, or the outcome that ultimately achieves all of the project requirements while optimizing the design. And that's where I would consider DfMA to sort of align and sit in. A metric I've tried to represent here, just a way to represent or how you might compare different options, particularly connections in this case. And this will make a bit more sense as we sort of work through this presentation. But the right-hand side represents 4 connection types that are essentially trying to achieve the same outcome, essentially beam to column connections. So that'll make sense, and you'll get an understanding of what the 1, 2A, 2B, and 3 types are as we go through. But what I'm trying to represent here is that idea of the project drivers and how they're weighted accordingly for a project. There's always, on every project, there's different drivers. I mean, a lot of the time, it is related to cost and time, construction time especially. They tend to be key drivers, but I'm just trying to emphasize here that there will be different drivers and according to different stakeholders as well. And so there's different weightings, and then you can actually relate that or correlate that with your individual costs per item as shown here. For example, CNC machining time, how that relates to cost and or time, connection time, procurement lead times or connection costs, so on and so on. And then coming up with a way that you can clearly see how they're compared on the right-hand side. So the bigger the value, essentially that's saying that that's achieving better DfMA outcomes. Now, I'm not trying to say, I'll just point out here, the item that says design requirements or robustness, I'm not trying to say that from one project to another, you can, skimp on the design requirements and not have a compliant structure or whatever the case may be. It's more around saying there may be specific projects that, for whatever reason, warrant greater robustness maybe, or more stringent design requirements. Maybe you're doing something quite unique or highly complex, or it's moving outside of what's been done previously to a greater scale or greater height. And everyone, to de-risk the project, you're putting more emphasis on those requirements or enhancing robustness and redundancy in the design. So that's what that is trying to say there. But if we look through, so changing the weighting of these, so from 1 to 2 to 3, you can see how that changes essentially the weighted score in the comparison table there on the right-hand side. And that's just a bit of a visual representation that I find somewhat useful. I think most people, including myself, tend to just do this mentally without having to put it down in a sort of a physical, tangible representation. But I just thought I'd share this as a metric that might be used, and I'll come back to this a little bit later on. So some of the things that I think are really important to highlight and to work to achieve greater design for manufacture and assembly outcomes are sort of standardizing and optimizing section sizes. But around standardizing the sizes, that allows greater nesting capabilities. So for press lengths, rather than having to have shorter press lengths and varying sizes, you can nest the same size members and cut that out of one larger press length, essentially. I'm not trying to say, though, that secondary elements that don't require to be as big as primaries, that you just use the primary size everywhere. Of course, that would be very inefficient and costly. So there's that balance. Finding that balance is pretty much the key across for all of these things that I touch on today. But this also has sort of tangible benefits in terms of handling, offsite in facilities as well as on-site, and even, loading and safety around loading trucks and ability to load those more safely if things are of consistent geometry. Hopefully that sort of makes sense to everyone. Likewise, when we look at plates and bracketry, standardizing those rather than making them unique for every single connection. And let's say you've got slightly reduced loads from one connection to the next, and you could effectively change a plate from 12 mil to 10 mil or something. It doesn't make any sense. It needs to be sort of understood that material efficiency alone does not produce, overall efficiency or optimization generally. Specifically with steel laser cutting, for example, they get cut out of big plates for the most part. So if you can standardize the plate thickness across the job where possible, or at least group those in larger batches to minimize just the variation in connection types and everything, that will actually achieve a better outcome than purely looking at material efficiency. Because what you'll tend to find is that by trying to do that and reduce things to the absolute minimum in each case, you probably end up with more waste, because if they're having to cut things out, or there's odd shapes cut out of a larger plate effectively, then yeah, that's going to ultimately go the opposite way to the intention. And I must say, generally, structural engineers are pretty good at this in the sense that they try to standardize things because they want to make their lives easy. They want to do one calculation that fits all. It can go the other way too. There's once again that balance between putting enough detail in and looking at things in enough detail and not just rolling out one sort of standard detail that fits all, because if there's slight geometric changes, which quite often happens, which is, you know, obviously tied into the shop drawing process and the point of that, but a little bit more thought in lots of cases can go a long way, and consideration early on, where sometimes, you know, a standard detail won't fit. So once again, it's about that balance. In relation to fixings, and I'll talk specifically about screws here, because that's typically, you know, what is used for the most part when we're looking at timber projects. And just to use this as a bit of an example, I'd recommend this type of thing is avoided, this approach. So specifying many screws that are the same diameter and slight increases or changes in length, you know, in the order of 20 or 50 mil increments from one to the next, just because there may be maybe it's a geometric change or a slight applied load change that means that you could actually slightly reduce lengths, or you may have to increase them somewhat. I would highly recommend that you try to standardize these and use one or a couple of screw types and lengths to suit as many applications as possible. This really de-risks the whole process as well, and it doesn't add significant cost in the scheme of the project. If you've got installers on site, you don't want to have so many screw types or fixing types on the job that it's confusing, things get installed in the incorrect place, and it's extremely difficult to pick up during inspections whether or not something has been installed in the incorrect place. I mean, screw heads will tell you the type and the length typically, but that's still hard to see, and sometimes things are covered up by secondary elements or tapes and things to provide temporary weather protection, or so on and so on. And sometimes these things can be missed. Probably more important when you get to this type of application. So once again, avoid specifying, where possible, partially and fully threaded screws of the same diameter and same length, because if, once again, someone just incorrectly reads the spec and looks at the diameter and length only, doesn't take any notice of the partially threaded or fully threaded specification, and they use these in, you know, let's say you're using a partially threaded screw, but that gets used in a connection requiring higher axial loads, or is used to transfer axial loads, and the fully threaded screws are only in shear connection, that's going to be a problem. And we all know that you can't really just remove screws, or you shouldn't. You can have great risk to sort of cross threading within the timber and completely, you know, getting far less capacity out of a screw if it's replaced. So it could be a costly exercise to make these changes on site if things are done in the wrong way. So anyway, recommendation would be to use different diameters and different lengths between the two. So there's a simple way to recognize the difference and identify them easily. And following on from that, try to avoid specifying screws that don't exist, like might be the type of head or the coating or a length that doesn't actually exist, or maybe they're low or out of stock. So please get in touch with your suppliers and get a good understanding of what's available locally, or lead times before specifying things. If you're needing to bring stuff in from Europe, for example, you've got 90 days lead time typically, and the alternative would be to air freight stuff in, which can be extremely costly. So just some advice there to try to minimize the number and type of fixings specified on the job, and once again, standardize these where possible. Okay, so to just go through some of these types. So this is type 1, which relates back to those sort of metrics I showed earlier in those bar charts. So just to run through some advantages and limitations of these. This is a direct bearing connection, and using our hardwood, both sort of regrowth and plantation hardwoods with greater sort of perp to grain bearing capacity, we're able to achieve bearing type connections without sort of reinforcement for the most part for most of the typical design solutions we're looking at currently in the industry. So some of the advantages are there's minimal CNC, that ties in with program efficiencies. There's minimal bracketry and fastener costs associated with this type of connection, more tolerance on site, and this enhances safety in design. I mean, you've got a physical bearing essentially when you're installing and assembling that beam to the column on site. So you're not relying on, the fasteners to take the load, especially, for construction loading. The support is as strong as it needs to be for the ultimate design case, let alone the temporary case in this instance. So there's, enhanced safety and design in that respect. Minimal assembly time, and no sort of pre-assembly in this case requirements, or very minimal. And I mean, prefabrication and timber in general, aligning with prefabrication processes always minimizes just things like noise, waste, and dust on site. But this in particular, without having to drive in Dowels and things like that, minimizes noise somewhat as well. Limitations architecturally, lots of architects to date, when these sorts of details are being proposed, are a little bit apprehensive to take them on. They're not super keen on that notched sort of seated detail. I'd really like, hopefully this can help convince them somewhat, just based on the comparisons that I'm showing here. But that's probably the main one. And then screw orientation is critical, but that's sort of mitigated by CNC. So putting in pre-drilling the holes, or at least pilot holes in the right orientation and location, means that there's sort of no risk, or very little risk, of those screws being driven into the char zone or through the face of the timber at the wrong angle. Now, if we look at what we've called 2A, so this is sort of a T-bracket connection. Apologies, I'll just quickly mention while I think of it too, the plate on top, we've shown that as a way to represent the robustness strategy. So, sort of tie forces, transferring those tie forces. Now, the assumption here is that would be consistent, and the requirement for that would be consistent across the board, or for all of these types. Therefore, we can essentially remove it from the equation in this case. So it has been considered, and it's, deemed to be consistent across the board, essentially. So yeah, this is a T-bracket with dowels and screwed to the column. The advantages are the bracket can be pre-attached to the column, so there's pre-assembly there, so it doesn't need to be done on site. And the top row of dowels could be designed such that they're pre-installed into the beam, so that you can reduce your hook time, essentially, so you're not having to get that in place, install all your dowels before you can unhook the member and go back and pick up the next one. Limitations, and this is all, once again, comparison to essentially the bearing connection, because we deem that to be the most optimal in this comparison here, or what we're sharing today. So there's considerable more CNC time with this, considerably more bracketry and fastener costs associated. There are architectural impacts with the plugging of dowels as well as cover plates. These sorts of things are pretty difficult to completely remove, and I'm sure most architects appreciate, given their experience with projects to date, that that's something that just has to be lived with. But it's just a limitation in comparison. There's more of those in this case. Dowels have negligible tolerance, so we're talking about 0 tolerance effectively in the timber, and +1 mil within the bracket. So that just really restricts, how well these can go together on site. If there's slight misalignments somewhere, these things are a little bit more difficult to drive in, and that can blow out your assembly times. And I just wanted to point out here, if this was to be mirrored across the other side of the column, you'd have to make sure the column was of adequate dimensions to avoid screw clashes and things. 2B, much the same as what I just discussed, the same advantages essentially, brackets pre-attached, first row dowels can be pre-installed. Through bolts would actually mean that if this was mirrored, you could just tie from one bracket to the next and design those bolts accordingly. And then in terms of limitations, once again, more CNC time in comparison to the bearing connection, greater bracketry and fastener costs, the impacts of the plugs and the cover plates. If this was an end or edge column on a project, you would also have the plugs on the column side too. And once again, Dowels present sort of negligible tolerance on site. So to show this as a sort of a comparison and to present some sort of real data, now I must, start with the fact that this is sort of optimized already and idealistic in the sense that the times put into the CNC, we've worked through, these are real times that we've actually run through our Hundiger machine files, and then the pre-assembly and side assembly times are sort of idealized in the sense that this means that everything has to go together really well on site and there's sort of no misalignments or nothing goes wrong. And the reason I want to emphasize that is that should, say, for 2A and 2B, there be misalignments in the dowels, for example, that might mean that you have to potentially drill out the plate, which takes time, but also may present structural issues, but it certainly has been done on jobs and needed to be done in certain instances. But the main point I want to address here is that that has an exponential sort of impact on cost and time on site. So even though you might look at this and go, oh, it's not a huge difference in terms of cost, if you extrapolated this out across an entire job and the risk associated with potential program delays, that's where the real benefits of a more optimized solution come into play. And this is where I'll just go back to the metrics that I showed at the start of the presentation to reiterate. You can see here that the bearing type connection, in terms of its ratio and cost, presents a far more sort of optimal solution. And that's shown all the way back here. Forgive me, let's run back here. You can see that regardless of the weighted scores applied, and all be them arbitrary and not sort of related to any specific project, but just for discussion purposes, the one in orange on the right-hand side, regardless of what the weighting is, you can see that that's still a clear winner. And it just really highlights the DfMA benefits of that type of a connection. I'll run back through here. I'm conscious of time. Definitely want Danny to be able to run you through some simulations and things to give you some further insight into how this all works in practice. So that's the point of these tables. And look, we could talk about this all day and go into this in a lot of detail, and it'd be a great sort of discussion topic, but please get in touch if you want to know more, or if you want to look at specific applications or projects that you're working through at the moment. Our team can provide great assistance with all of this. Here's just one that I'll quickly go through. This one's less sort of clear. There's no real front runner, and I must let you know that 4A is once again a bit more for discussion purposes than anything. Apologies, I'll go back here. I forgot to mention the beam to column continuous option. Once again, that should actually be halved, because you're effectively achieving 2 connections in that instance rather than 1 like the rest of them. I did mean to go through and halve that, but I didn't get around to it. So you could say that that's a ratio of 1.6 in that instance. And this just once again highlights the benefit of utilizing our hardwood and the perp to grain capacities of that without having to reinforce the timber. So these things can be done and are being done with some softwoods, but you have to reinforce both the beam and provide a way to distribute that load to the columns in most applications. So back to these splices, once again, these all sort of look comparable when you look at this table in isolation. The point would be, back to those drivers and design requirements. You may choose to use fully threaded screws like 4A and 4B to enhance connection stiffness. Maybe you're wanting to limit how much deformation you would get at a joint. And then say 5A and 5B, the main probably takeaway here is if you've got adequate timber width, which in this case we're looking at 210 wide members, so it's still quite narrow, and that's just once again sort of the benefits of Ash's hardwood, that we can reduce member sizing accordingly. But you actually achieve through the connections, if you're using 2 flitch plates compared to 1, you're reducing time, and you're also once again reducing risk. If there's any misalignment, you can see 5P, there's significant quantities of Dowels on that. So if something is misaligned, that's once again just exponential in terms of the rework or rectification works required, or the time it takes to get everything to align, and the flow on impacts of that across the job, can be really problematic. So they're the things that you need to keep in mind here. Granted, once again, looking at this at surface level, it doesn't look like there's any great difference, but you need to factor all these other things in. And once again, this is all sort of idealized. This doesn't account for other things like crane costs and all that. So please don't call up and abuse any installers if you think that they should be, if this looks cheaper than anything like that. And I don't want anyone calling me accordingly. There's other things that haven't been considered here, and it's just purely for comparison's sake. So in terms of, I guess, takeaways from today, from my perspective, please collaborate with other stakeholders to understand the objectives and to enhance DfMA where possible, and use your suppliers to assist with the optimization of design and detailing. Our team loves to get involved as early as possible and really facilitate that throughout the entire project as well. And at the end of the day, it makes everyone's lives easier by collaborating accordingly. So yeah, thank you. I'll let Danny take over now and show you some more visually stimulating stuff.
I thought we'd just try something a little different and show the design process behind our sort of CAD and CAM processes. So this is how we're CNCing and dealing with all the design issues. So essentially we're using CAD work here to do all of our modeling. The reason we're using that is for accuracy and the ability to talk to the CAM software that we use as well. So it's a little bit different to your typical sort of Revit ArchiCAD in that it's not so much specifically for renders or layout or that kind of thing. It's really to be able to talk to the machine. So for instance, we've got the bearing connection here, which also includes fire tape as well to different char depths, which the hardwood tends to do quite well in as well from increased density. And it's really about modeling every screw, every dowel, exactly how the machine's going to be able to interpret it. So when we do connection design, we look through each of these and model them to what the structural specifications required, but we're also thinking about how the machine's going to interpret the most efficient way to get through it to reduce CNC time as well. So for some of the more complex ones, might notice that some of the slots are a little bit bigger. That's because we're thinking ahead to what the machine requirements are. And we've got a smaller slot on one side than we do on the other side as well too. That's to allow for things like radius of tooling, tolerance on site, and that kind of thing. So when we put all that together, we'll have a manufacturing model. Each of these pieces will be given individual information. So that allows for things like site installation sequence, CNC manufacturer, even down to what pack, what truck, and the sequence that they're in as well too. So it's really down to every single screw, every single dowel as well, and to look at visual impacts as well. We'll put in cover plates with rounded corners to suit the mill on the machine and deal with all of that. So we'll jump into a simulation. You can see that. So this is using Cambium software. So this does a lot of our CAM work. Basically bringing this in from CAD work, we can run simulations on the parts, have a look around the machine to see how that's going to work, what the most efficient way to cut through and deal with all of that is. So you can see in this part, this is for one of the bearing beams. So it's very limited CNC work. It will only take probably about 11 minutes. The process here, we've got initial cuts through the tooling, although it's lost the first part of that. Yeah, I'll jump to the next one. Basically, this allows us to look through the tooling to see what's efficient, but also gives us a visual impact as well of what it's dealing with. So for instance, in this particular one, this is for the T-bracket beam. So we've done an initial cut with the V tool. The issues that we sometimes have with hardwood is that because it is a little bit harder, it becomes difficult with things like tear out and drilling from both directions. So to compensate from that, we've got a few different tools here. This is doing the drilling from underneath. Compensate for that. Let's go forward a little bit. Yeah, okay. So in particular, this shows the order of operations that we might do things in. So we've got a cover plate to the bottom, which we're going to do first because that'll stop the tear out when we do the through slot as well too. So you can see as well after this, it'll run through to the milling. So we've got for the weld recess on the back side there. We've got fire tape recess as well. Run through, and then finally, after that's completed, it'll run through to the main saw unit, which will do the through slot. So essentially, we've got a few different types of slots that we typically do. We've got through slot, which is being shown here, where the saw runs all the way through. That's the most efficient way to get rid of the material. But we can also do restricted one-sided slots, which are a bit more like the one shown here. So it needs a cover plate to one side, but what it allows us to do is go in with the saw, clean it up with the chainsaw afterwards. We can also do blind slots, but that is using the chainsaw more than we would otherwise like to. So I'll jump into the last one. So this is for beam splice. It's at the moment processing an initial cut, which it will then reference off. And from here, you can't quite see the bottom one there, but what it's actually doing here is we're drilling from both sides. So we've got a revolving unit at the top and underneath the combi support vertical. So what that allows us to do is to speed up the process of drillings, especially when there is multiple dowels, as Nathan pointed out earlier, allows us to do them at the same time. And it also means that we're not getting tear out when that drilling is punching through the top surface as well. Let me skip forward. Essentially all these processes, depending on how complex one piece is, like we showed with the bearing connection, that can maybe have 30 processes, but we've had ones for the Latrobe trees, which Joel, our other engineer, programmed in, and I think that had something like 400 processes as well. So they're ordered in a way that makes sense for the machine to be able to handle it, but also get the best product out of it and not get too much tear out. So at the moment here, it's doing cover plates to the bottom. So it's using the 40mm mills. So that means the radius for the matching cover plate also has to have a 40mm radius on there as well. So we skip forward here. So on the other side, and then we'll jump in with the saw cuts, I would imagine. So first of all, taking as much material as we possibly can with the saw, and then it'll be jumping in with the chainsaw to finish the rest of the slot. So yeah, we have using the robot chainsaw, which is a 7-axis unit, so it can do on the angle as well. So we have 2 units here. We've got one at the front dealing with these slots, and a fixed axis slot cutter at the back, which has a larger radius on it as well. So that's basically just taking out the material that's right in the corner. So in here, that would be the material that's coming out here in the corner. The other option is that you provide a relief cut to the steel as well. So it's a couple options there. But essentially that's our process of taking it from CAD work into Cambium, dealing with CAD, and then going into CAM as well too. So
yeah, I think it's just worth mentioning too, Danny, that big part of the DfMA, you know, or the desire to achieve DfMA is to really understand the machining capability. So you can head to our website, and most suppliers will have some documentation, or get in touch with us to really understand our tooling and the capability in terms of depth of cuts, radius of saws or millings, or drill bits and things like that, so that you can design with that in mind from the start rather than changing. And same with probably Dowels is a good example, with sort of the limited tolerance with those. Going to say a 20 diameter dowel tends to be better to avoid deviation in the actual drilling, especially if you've got wide sections, just based on the length of those drill bits and everything, especially in the density of our hardwoods. There can be some deviation, especially with smaller diameter drilling. So that's really important too. But please, once again, get in touch with us and we can take you through all of this in more detail. So yeah, look, let's open up questions, I guess. Alistair, if you want to jump back on.
Thanks for that, Nathan and Danny. That absolutely amazing presentation. So yeah, and fantastic to see those the way you're doing it there, Danny, and all the technology. I mean, when you think of what hardwood sawmilling used to look like, it's a completely different environment now with the manufacture and just amazing sophistication. So well done to you to both. Now we have got some great questions coming up. I just wanted to actually ask one up front, Nathan. When you're thinking about dowels or screws, I mean, but how are you prioritizing that? What's your thoughts about when you use a dowel and when you use a screw, and who makes that decision? Is that sort of something you guys would make, or is that something the engineer or architect would have a view on?
Typically the engineer drives that decision more often than not, based on just the connection design. It's rare that, well, I haven't seen too much pushback. Danny, feel free to jump in. Bolts, maybe due to plug sizes, can be problematic, but they provide so many other benefits. So that's always, especially in regards to tolerance and assembly requirements. But architects may take an issue to larger plug sizes and things for bolts, for example, because you've got a larger washer. But with, say, dowels and screws, it is typically driven by the structural engineer. We really try to work with engineers if a project is already sort of well into design development to rationalize these things and work through them and get them to understand the issues around, especially say you have quite a deep section, and if you have any sort of fixings, but say dowels across the entire depth, what are the issues around movement in service, and is that going to potentially initiate any sort of checking because you're restricting that movement over a larger area and these sorts of things. So yeah, the stiffness and everything comes into play. Of course, you know, ductility, if that's driving things, is of course an important structural issue as well. So it's about understanding the drivers and the requirements of these connections and trying to optimize it accordingly.
Yep. And you were speaking earlier on about the do's and don'ts with screws. A question there about, well, what are the common sizes and lengths of screws you're generally using?
It really depends. I guess with our hardwoods, it depends on, well, firstly, the application. But if we think about just say fixing, let's focus on, I don't know, a tensile connection, for example. If we're fixing through a steel plate, you tend to find that, I don't know, in the order of 260 mil or whatever in terms of embedment, might even be less in some applications, you're actually maxing, or your governing capacity is the steel failure of the screw rather than the embedment strength. So that's where sometimes we'll see much longer screws probably coming off the back of what's been done previously with softwoods in mind, and they're, you know, sort of a copy paste job of this detail we've used before, so we'll copy it across, and the requirements to then pre-drill, and obviously, you know, the installation effort because of the torque requirements is higher. There's no denying that. You're going into denser material. So that's where, yeah, all of these things need to be considered, but it really is, it's hard to give a generic response to that. So in terms of the screw sizes, it really does come down to the specific connection we're looking at. So
thanks for that. And Jack just comments about the bearing connection looks really great. Is there a reason we haven't seen it as much in the US market compared to, say, the US?
So here, I mean, I've personally been trying to push this for many years. There'd be hopefully some people attending that could attest to that. I mean, Danny's seen it even in my previous role at Riztex and stuff come across his desk, and the Ash team prior to myself joining, been really trying to push that. I think resistance to unknowns and also these sort of architectural concerns. But we're about to see, and you know, Jack's mentioned this probably for a good reason, we're about to see some of these go into practice on a pretty big scale. So the proof will hopefully be in the pudding, as they say, with that. And it'd be great to see if all of what we're talking about here is actually achieved with these connections. I'm not sure why there's resistance to this type of connection. I mean, we're utilizing the material in the way it should be utilized. We're using the properties and the benefits of those properties accordingly. So it makes perfect sense to me.
Just on that question, there's a question here about bearing. There's a question here from Troy about your version 1 connection. Could the bearing portion be mitered at, say, 45 degrees? You want to comment on constructability and cost or a benefit there?
Yeah, there'd certainly be issues around how effective that bearing is, and in terms of any slip and the temporary sort of support, I guess, of columns and things to prevent, you know, things pushing out effectively because of that resultant in the sort of the span direction. Could be looked at in terms of constructability and cost. I think obviously it's not as easy to construct for those exact reasons I've just mentioned there. Cost-wise, I can't imagine it's going, if I'm understanding what the proposal is, to rather than a perpendicular seat, we're talking about 45, unless I've misunderstood that. Yeah, I don't see the cost being greatly reduced because of that. The machining requirements would be much the same, I would imagine, if not probably more difficult due to the inclination of that cut.
Thanks for that. And a good question here from Nick Hewson. There's a number of people have liked this one because it does come up quite a lot. Nathan, can you comment more on the fire performance of the beam to column connections? This seems to be increasingly a sticking point to resolve with many consultants, so demanding expensive full-scale fire testing for specific projects. Yeah.
Look, I don't see a lot of sense in having to test every unique connection on every new project. It makes zero sense to me. We've had the codes for Glulam in particular for a long time and been using that. Granted, it's a different scale, but I think there needs to be that differentiation between the objective of a fire test. Are you testing a connection because you're worried about the connection, or are you testing it and trying to extrapolate that to some sort of burnout, outcome, or, justifying whether there's self-extinguishment or burnout? And I mean, for that, you really need to do a full-scale compartment test rather than the connection alone. If we're designing these connections as we are, with adequate char zone to protect all the connection or the bracketry and fasteners, I don't see how that's not already code compliant. And I mean, the fact that we've done so many, and Nick's obviously been a big part of so many previously, I'm not aware of any really failing to date or that haven't achieved the FRL. So I'm not sure why we're having to do so many. I think it's once again just this, everyone's a little bit concerned as we start to get into this space more and more, and we ramp up with more and more buildings, which is okay, but there needs to be a point where we have some confidence. And I would suggest that we should already have that confidence, especially we're looking at jobs where we've already done tests on probably more critical connections previously. Why are we now testing something that's clearly got more inherent safety and design, or, cover and protection in a fire case? It should be, you should be able to interpolate from there or extrapolate accordingly.
I think you're right there, Nathan. I think people, particularly the regulators, are becoming more sort of confident now and comfortable as they see more of these buildings produced. Just a question for you, Danny. In terms of the programming, the CNC machine, do you need to do that for every beam and every connection, the way you've shown us? But it's amazing the stuff you've been doing.
Yeah, that's right. So it just highlights the advantages of modular design as well too. When you're making connection details the same, makes it easy for the engineers, makes it easy for the architects, but it also makes it easy for us. It's less drawings, it's less files to be able to make, and then it's also reducing that risk of potentially getting details wrong on site when there is a screw that's 320 long or 300 long. If you're standardizing things, it means that production throughput is going up because you're really just producing the same thing, much like a manufacturing line. So yes, does have to be a new file for every different piece.
Every instance of every change, essentially. So that, talking about, well, when I spoke about member sort of standardization, if that also includes the connection details at the end, then that's one file that might cover, 50 members on a project.
Just looking at the sophistication of how the machine works and the things it does, it just does illustrate your comment you made up front, both of you, about how important it is to have you guys involved early in that sort of design process, understanding how the tools work. I mean, do you want to just talk a little bit more about that and how you found that to be critical with projects today?
Yeah, for sure. It makes all the difference, really. I mean, we can have beams or columns that take multiple hours on the CNC machine, or as you saw before, beam can take 15 minutes. And really the detailing around that, there is, as of course Nathan's gone through, trade-offs in terms of connection costs, ease of installation and all the rest of it, but the CNC part of it too. Just some little clever tricks and tips along the way, and acknowledging for things like hardwood that is going to be different to softwood in terms of drilling and milling as well, makes all the difference really there. So having that in the back of the mind as well too, and also thinking ahead towards installation as well, because there's no point making something that's going to be hard to put together.
A couple of good questions here from Jeremy Church, which is not surprising. Is there a requirement to pre-drill screw fixings given the density of Australian hardwoods? I guess we're sort of used to doing things with softwoods, but hardwoods are a little bit different.
Yeah, definitely. Essentially all of them need to be pre-drilled, except, I mean, there are screws on the market, say, just to use the example that's quite common, where you have a CLT floor going into the glue laminated timber using appropriate screws from specific manufacturers and or their hardwood screws. Might mean that you don't have to pre-drill those applications, but typically for the GLT to GLT connections we've been talking about, we do pre-drill all of them. And it prevents, you splitting and everything like that. And it's a very expensive member to rectify should something go wrong. So it's worth de-risking it from that perspective.
Well, that's actually a sort of good segue into the second part of Jeremy's question here about to minimise any issues on site. Can you please explain your QA system and approach? So presumably more complicated connections require more rigor and time and integration in the factory to avoid any downstream impacts.
Correct. Yeah, exactly what Jeremy's mentioned there and alluded to. That's exactly right. And they should be given more weight on site in terms of inspections and everything. I would suggest that they probably aren't. It's probably, you know, that's a different topic for another day, but yeah, they do take longer to inspect. And there's also the risk of how do you inspect some of these? If it's a complex design that then is completely concealed and hidden, how do you actually check that it's gone together correctly? You're relying on, you know, an experienced installer letting you know that, you know, it has gone together correctly.
A couple of questions here around bolted connections. So is there a preference for screw connections over bolted connections? And if so, what are the main drivers for using screws?
Look, it really depends on the application. Bolts have huge benefits in terms of tolerance and ease of assembly. They do require more machining. There's no denying that. So that's where there's that trade-off. It does really come down to the application. There's also space requirements. Obviously, you're using bigger fixings, therefore the spacing, end distances, edge distances has an impact that may lead to increased eccentricity. So therefore, you've got to account for that. Trying to think of a specific example. It's difficult to say without say something we're looking at typically, but if we just take those T brackets, for example, it could be a way to, provided you had adequate width so that you could actually recess the bolts and the washers accordingly outside of the char zone or within that and still have enough shank and thread length to provide adequate bearing to achieve the capacity in comparison, say, to a dowel. There's benefits in that for the tolerance reasons and things, for things to go together on site more easily. It also means that there's more allowance for movement in service. Like I mentioned before, even though, you know, look, these connectors are pretty ductile, so usually there's no major issues there, but that is a small advantage. And then say over screws, I mean, that's where typically we find there's only really, say, that through bolt type where you're using screws compared to bolts in that application. That's where they sort of come together relative to other applications where it's a bit more difficult to actually use screws. Like you can't, you know, unless you're using self-tapping dowels, which, you know, are problematic in themselves sometimes and, you know, can be time consuming to install. There's not always that clear comparison between screws and bolts and or dowels for that matter. But yeah, look, once again, get in touch with us for some specific connection details you're looking at and we can come in accordingly.
Someone just wanted you to clarify, when you're using dowels, how do they stay under the timber? Do you use glues at all?
No, so that's the whole purpose of tight fitting holes. You're relying, like they are smooth, so there's minimal sort of friction essentially, but they're tight fitting so that they form a bit of a wedge, and under load they will lock in because there will be that deformation through the plate and everything. Plus we're gluing in plugs. More often than not, we're having plugs of some description, whether there's FRL requirements or not. But when you do have, say, 60, 90 minute, 120 minute FRLs, you've got a decent plug that's glued in to hold that in. And dowels should only ever be used in concentric connections for obvious reasons. There's no sort of withdrawal capacity, or it's, you know, there is minimal withdrawal capacity, but there's no sort of threaded element or glued element to it.
Yep. Tom asked, does the bearing connection also have a higher degree of cost certainty when looking at pricing jobs?
100% it does. And especially in this market right now with the fluctuations in fuel and steel prices and all of the above and everything in between, there's huge uncertainty from the time that we initially quote a job to the time that it actually finally is about to go into construction. Usually there's significant fluctuations in these things, and either we have to put enough margin on to cover ourselves, therefore there's, you know, uncertainty around cost, or we end up, you know, just wearing it, unfortunately. So when you can simplify connections, take elements out of it and still achieve, you know, ultimately the design intent, that's always better and going to give you more cost certainty for sure.
Fantastic. Look, we're just on 12 now, so we will have to finish up there. So Nathan and Danny, thanks for a fascinating presentation. That's been terrific today. I just remind everyone that the events are recorded, so that if you want to go back and relook at this or recommend it to a colleague, just go to our web page, go to the webcast and presentation section, and all of those presentations are available. So our next webinar in 2 weeks' time is going to be the first of a series of 3 around AS 1684. I know there's a lot of interest in our residential timber construction code. So our first one will be presented by Lex Somerville, looking at general usage and applications on the 12th of April. And then over the following 2 months, or after that, we'll be also covering then bracing, design, specification and detailing with Afsal Lafia, and then tie downs and connections with Tim Rossiter. So they'll be effectively 1 a month. So in between those, obviously fortnightly, there'll also be some other webinars on some other topics. So something to look forward to. So thanks once again, guys. Really appreciate the time and effort you put in here, and as I am sure do all the rest of the audience today. So have a great day, everyone. We'll see you again in a couple of weeks' time.
Thanks, everyone. Thanks for tuning in.